star has been a source of wonder and fascination for millennia. Its immense heat and light sustain life on Earth, but beneath its fiery surface lies a complex composition that raises intriguing questions about its elemental makeup. One such puzzle revolves around oxygen, the very element essential for life as we know it. If the sun is so hot, where does it get oxygen from? This question delves into the heart of stellar astrophysics and requires an exploration of the sun's formation, nuclear fusion processes, and elemental cycling. To understand the source of oxygen in the sun, we must first examine its formation. The sun, like other stars, originated from a vast cloud of gas and dust, known as a molecular cloud. Gravity gradually pulled together the material within this cloud, causing it to collapse and form a protostar. As the protostar contracted, its core temperature rose, eventually reaching a point where nuclear fusion reactions ignited. At the core of the sun, temperatures soar to millions of degrees Celsius, creating an environment conducive to nuclear fusion, the process by which lighter elements combine to form heavier ones, releasing vast amounts of energy in the process. The primary fusion reaction occurring within the sun is the conversion of hydrogen nuclei, protons, into helium nuclei through a series of steps known as the proton-proton chain. However, oxygen is not directly produced through these reactions. Despite the absence of direct oxygen production in the sun's core, oxygen is present in its outer layers. The sun's composition, like that of most stars, primarily consists of hydrogen and helium, with trace amounts of heavier elements such as oxygen, carbon, and nitrogen. These heavier elements are thought to have originated from previous generations of stars that synthesized them through nuclear fusion processes during their lifetimes. When these stars reached the end of their lives and underwent supernova explosions, they dispersed their enriched material into space, enriching the interstellar medium with heavier elements. The presence of oxygen in the sun can be attributed to a phenomenon known as elemental cycling. As stars like the sun evolve, they undergo processes such as nuclear fusion, convection, and turbulent mixing, which transport material from their interiors to their surfaces. This material may include heavier elements like oxygen that were synthesized in the cores of earlier generations of stars. Over time, these elements become incorporated into the outer layers of the sun through processes such as stellar winds and mass loss. One mechanism by which oxygen and other elements are transported from the sun's interior to its outer layers is through the solar wind. The sun continuously emits a stream of charged particles, including electrons, protons, and heavier ions, into space. This solar wind carries with it a fraction of the sun's elemental composition, gradually enriching the solar atmosphere with heavier elements like oxygen. While the solar wind primarily consists of hydrogen and helium ions, heavier ions such as oxygen can also be detected within it. Observations of the sun's atmosphere, conducted using instruments such as spectrographs, have provided valuable insights into its elemental composition. Spectroscopic analysis of sunlight reveals the presence of absorption lines corresponding to various chemical elements, including oxygen. By studying these spectral lines, astronomers can determine the abundance of oxygen and other elements in the sun's outer layers, confirming their presence despite the predominance of hydrogen and helium. In conclusion, while the sun's core is primarily composed of hydrogen and helium, with nuclear fusion reactions driving its energy output, oxygen and other heavier elements are indeed present in its outer layers. These elements are thought to have originated from previous generations of stars and were transported to the sun's surface through processes such as elemental cycling and solar wind ejection. Understanding the origin and distribution of oxygen in the sun not only sheds light on its complex composition, but also provides valuable insights into the evolution of stars and the